Hello student, today I am going to start a new chapter, electromagnetic induction. Okay. Now first you have to know what is electromagnetic induction. Now in electromagnetic induction, if a coil or closed loop is placed there and if we move the bar magnet like this, then there is a change of magnetic flux, and this change of magnetic flux link with this coil, and due to this phenomena is called, due to this induced EMF or current produced through this coil closed loop. This phenomena is called electromagnetic induction. So before knowing the electromagnetic induction, you have to know magnetic flux. What is magnetic flux? Now I already discussed what is electric flux. Magnetic flux is like that. It means suppose there is a coil is present like this and a magnet. This is bar magnet, this is north pole, south pole. We know that magnetic lines of force starting from north pole and ending at south pole. Now if we hold this, now the magnetic lines of force passing through this coil, when it is held normally, in that condition the total magnetic lines of force are called magnetic flux. Okay, so here it is written magnetic flux. So magnetic flux generally denoted by phi letter. This is magnetic formula. It is equal to vector B dot vector A. Vector B is magnetic lines of magnetic fields and A is the area vector. So it is the dot product. So according to dot product, phi equal to BA cos theta. This is the area vector is always, direction of the area vector is always perpendicular to the normal to this area. Okay, that is its direction is shown by this line. Okay, and this is the direction of magnetic field. So angle between magnetic field vector and area vector theta. So this is the formula to find the flux through a surface area when it is held normally. Means okay, so phi equal to vector B dot vector A equal to BA cos theta. Now electromagnetic induction already discussed. Now see in this figure, now when a bar magnet, this is north pole and south pole, moving towards a coil, in this circuit one coil is connected with a galvanometer. There is no source of EMF. So when we will move, what happens in this circuit, we show that galvanometer will deflect either along this direction little or this direction. It means we know galvanometer only detects the flow of current. So it means whenever we move a bar magnet very close to the closed loop or closed coil, then the current will produce. That current is called induced current, and as we know that current produced due to induced EMF, so here the produced EMF is called induced EMF. Okay, now it happened due to Faraday's law. Okay, Faraday experimentally observed this thing and he puts this observation in three laws, in the form of three laws. The first law, according to Faraday's law, whenever magnetic flux link with the coil changes, means this induced current or induced EMF produced whenever the magnetic flux link will changes with the coil, then only induced EMF or current produced. Second one is induced EMF or induced current last as long as magnetic flux changes. It means induced EMF or induced current last as long as magnetic flux link will changes, otherwise it will not last long. Okay, and number three, it is very important, the magnitude. Remember this magnitude only. Magnitude of induced EMF is directly proportional to the rate of change of magnetic flux. Now induced EMF generally denoted by E, small e. So according to third law, E equal to d phi dt. Okay, or you can write phi 2 minus phi 1 by t. So this is what a rate of change of magnetic flux is directly proportional to induced EMF, or induced EMF is directly proportional to rate of change of magnetic flux. Magnitude only, and direction of the induced EMF or induced current is given by scientist Lenz. That law is called Lenz law. I will discuss later on. Okay. Now, experimentally, how Faraday demonstrate. Now see, in figure 1, this is figure A. This figure, in this figure A, it consists of one coil and one galvanometer. Okay, G for indicates galvanometer. It is connected. Okay, and it is closed. Now, if we place a bar magnet which consists of two poles, north pole and south pole, like this, like as it is shown in figure A, here both are stationary. Okay, means neither coil is moving away from the bar magnet or towards the bar magnet, or this bar magnet is not moving towards the coil or away from this coil. Both are fixed. So he observed that there is no current flowing, means galvanometer needle does not move in either direction. It means there is no current flowing through this closed coil. Okay, but in figure B, when this bar magnet is moving towards this coil, okay, then galvanometer needle deflect along this direction, suppose. Okay, and as we are moving this bar magnet like this, as it reaches closest to its needles move more deflect. It means current increase. So whenever this bar magnet is moving towards this coil, the current is produced here. Okay, this current is called induced current, and EMF produced due to this movement of this bar magnet is called induced EMF. What happened? We know that this is the bar magnet, north pole and south pole. This is the line of magnetic lines of force. So whenever we are moving this bar magnet like this, what happened? The magnetic lines of force link with this coil. Okay, and it is changing. So a induced current will produce here. Similarly, when we move away this bar magnet from this circuit, coil circuit, along this direction, moving away, what happened? Magnetic lines of force linked with this coil will changes. Okay, so with respect to time, so induced here also, needle of the galvanometer will deflect, but in opposite direction. So here current is flowing in opposite direction. So whenever in this experiment, simple experiment, we have observed that whenever magnetic flux link changes with respect to time, then only induced EMF or induced current produced. Okay, so this is the basic experiment. I will just go through this, and later on I will discuss about Lenz law and different types of how many ways we can change the magnetic flux link with the coils. Okay, so for today's class only, we just go through these things only, and I will give some notes and you just go through that notes. Okay.